Good morning, students. Dear students, as in the previous video, that is part 16b of chapter 5 laws of motion, we had discussed about the various type of frictions, in which we had discussed about the types of kinetic friction. And while discussing about the types of kinetic friction, we had discussed about the sliding friction. Then we had discussed about rolling friction. After that, we had discussed about how sliding friction is converted into rolling friction, and what are the advantages of converting sliding friction into rolling friction, how sliding friction is converted into rolling friction. And one interesting example, we had discussed that why it is easier to push a long roller than to pull it, and mathematically we have derived the condition also. We have derived the condition for rolling without sliding. All these things we had discussed. Now, in the today's video, we will discuss about the interesting two application of friction, that is the motion of a car on the curved road, and the second thing we will discuss about the motion of a car on the banked road. Before discussing these things, I want to discuss about the dynamics of circular motion. So let us start our discussion with the dynamics of circular motion. So dynamics of circular motion. Dynamics of circular motion. Dynamics of circular motion. In the previous cases, we had discussed about the circular motion, in which we had discussed that if a body is performing a circular motion or moving along the circular motion, so this is the center O, and suppose the body is moving in this direction, suppose this is V1, then at this time this is V2. Means at each and every moment of time the velocity is changing. So you know that the acceleration of the body which is moving on a circular path, then if we want to know the acceleration, then we have to translate the tail of this v1 vector with the tail of this v1 vector with the tail of v2 vector, and it will be like this: v2, v1, and this is delta v. This thing we will get as delta v. That is v1 plus v2 is v1 plus delta v. The delta v is equal to v1 minus v2. That is, change in delta v is the change in velocity. Delta v is the change in velocity. Clear? The direction of this change is toward the center. Direction, look at here, if we translate, so this is toward the center of the circle. This is toward the center of the circle. So we can say that if a body is moving in a circular track with velocity v and has a radius r. The circular track has the radius r and it is moving with velocity v. Then the acceleration towards the center of the vehicle moving the circular track, that acceleration is called as centripetal acceleration, and it is given by v square upon r, as we had calculated before also. So this is called as centripetal. This is called as centripetal acceleration. This is called as centripetal acceleration, and it is directed towards. It is directed towards. Directed towards the. It is directed towards the center. But all of you know that by Newton's second law, F is equal to m into it. F is equal to m into it. And here, look at here. If the body is in this circular path, look at this circular path. If with the different time interval, if the body is changing its velocity as the time increases, means for the change in velocity, as you know that for the change in the velocity, a certain force is required, or a certain force must be exerted on the given body. Means some force is responsible for changing the velocity of the body on the circular path. So that force, I suppose by Newton's second law, that force Fc is equal to mac. That force, now putting the value of mac here, it will give mv square upon, and this mv square upon r is called as Fc. It is called as centric. This is called as centripetal force. This is called as centripetal force. And since, as the name clears, centripetal force means this force is directed towards the center. This is, if the force is whatever the direction of acceleration, and in the same direction of acceleration the force is being applied. So the direction of force is also towards the center of the circle, and so it is called as centripetal force. Now we will discuss what are the different causes of the centripetal force in various cases. Suppose I am taking case first, and in case first, what we are saying that, suppose you had, this is center O, and you had word a stone. This is a stone. This is a stone which is tied with the rope. This is a stone which is tied with the rope. Now you are moving the stone in like this. You are moving the stone like this in the circular path. Then the centripetal force in this case is provided by the tension produced in the string. The centripetal force is provided by the tension produced in the string. Case second, I am writing here. Case second. Another circular motion, that is motion of a planet orbiting around the sun, or motion of the satellite orbiting around the moon. So suppose this is the sun, which is situated in the center, and there is a planet P which is moving in the circular path around the sun. So the centripetal force for the circular motion, that is Fc, is provided due to what? Is provided due to the gravitational pull between planet and sun. Gravitational pull between planet and sun. This is the cause of centripetal force. When a planet is moving in the circular path around the sun, the cause of centripetal force is the gravitational pull between the sun and the planet. And the third case is that Case third. Case third. A cyclist, case third is the cyclist moving on a circular track. Suppose this is a circular track. This is a circular track. And on this circular track, suppose there is a car. Suppose this is a car. And this car is turning on the circular track. Then this is the center of the circular track. So the centripetal force for providing the circular motion of the car on a circular track is provided by the force of friction. The force of friction between the tire and the road. The force of friction between the tire and the road, which acts as the centripetal force for the circular motion or motion of the car on the circular track. So, a smaller frictional force provides the centripetal force. Sorry students. Now dear students, look at this numerical. But before discussing this numerical, one thing I want to mention you. As we had studied that the centripetal force is mv square upon r. Centripetal force is mv square upon r. But while discussing the circular motion, statics of circular motion, we had seen that v is equal to velocity v is equal to omega into 1. Velocity v is equal to, that is linear velocity and angular velocity. Angular velocity into radius r gives the linear velocity. So we can write here as m r omega square. Clear? Means what you can do this? Look at here. You can write here as m r v square upon r square. This thing you write, and from here m r v upon r whole square, and v upon r whole square is equal to omega, so we can write it as fc is equal to mr. So this is the another formula which is relating the centripetal force with the angular velocity. Here centripetal force is related with the linear velocity, and here centripetal force is related to angular velocity. Now dear students, look at the numerical in front of you. In this numerical, it is given that an artificial satellite of mass 2500 kg, artificial satellite of mass 2500 kg, mass of the artificial satellite is 2500 kg, is orbiting around the earth with a speed of v. It is given v is equal to 4 km per second, means 4 into 10 to the power 3 meter per second, and at a distance of 10 to the power 4 kilometer. At a distance of, means r is equal to 10 to the power 4 kilometer, means 10 to the power 7 meter. Calculate the centripetal force. You have to find out the centripetal force. We have to find out the centripetal force. Fc is equal to mv square upon r. So all things are in SI. So 2500 into 4 into 10 to the power 3 whole square upon 10 to the power 7 Newton. Now 25 into 4 16 into 10 to the power 8 upon 10 to the power 7. It is equal to 400. 4 into 10 to the power 10 upon 10 to the power 7. 4 into 10 to the power 7, and it is equal to, it will cancel out and it become 10 to the power 3. So Fc is equal to 4000 Newton. Centripetal force is equal to 4000 Newton. So this is simple numerical based on the formula. Now dear students, we are going to discuss the interesting topic, that is interesting application of laws of motion, circular motion of a car on level road, circular motion of a car on level road we are going to discuss. So now dear students, we will discuss about circular motion of a car on level road. So try to understand what is the condition and how it is happening. It is very much interesting to understand this fact. Suppose this is a level road and the road is curved here, and look at here. Suppose this is a car, and this car is taking turn on the circular road. So look at here. There is a normal reaction. Normal reaction R is acting due to the level road, and mg is the weight of the car on the level road. If the car is moving with velocity v, and suppose this is the center of the curve, and this is radius r. Clear? Now dear students, as I had told you before while talking about the dynamics of circular motion, that in case of turning of a car on the level road, the centripetal force is provided by the friction between the tires, the frictional force between the tire and the level road. So the frictional force is provided by the friction between the tire and the level road. Now we can resolve the forces since there is no any velocity or no any movement of the car in the vertical direction, since there is no any motion in vertical direction, So R minus mg it is equal to 0, or you can say that R is equal to, and we consider it equation number 1. Now dear students, now understand here, if suppose if this curvature is not there, if this curvature is not there, or if this is the curvature and the road is smooth, there is no any frictional force, in that case what will happen? The car tries to maintain its impending motion. Whatever the motion the car is continuing, that is, car is coming from the straight, it tries to go away from the road. It tries to go away from the road. But the frictional force, which is providing the centripetal force, that frictional force which is providing the centripetal force makes the car to take a curved turn, makes the car to take the curved turn. So you had observed that what will happen here. Look at here. The centripetal force is what? The centripetal force mv square upon r. This centripetal force tries to, this centripetal force is provided by the frictional force, and this centripetal force must be less than or equal to the frictional force, must be less than or equal to the frictional force. And this frictional force is given by what? This frictional force F, that is given by mu s into r. In case of a static friction you had studied. So from here we can write it as F is equal to mu s into r. Or r is normal reaction we had calculated. So F is equal to mu s into mg. F is equal to mu s into mg. Now understand the concept behind it. Suppose this frictional force is less than the centripetal force. The centripetal force means this frictional force is not providing the sufficient centripetal force to take a turn by the car. This frictional force, again I am saying, this frictional force is not providing that much amount of force to maintain the circular path. Then this frictional force is less than mv square. If mv square r is the centripetal force which is responsible for moving the car on the circular track, which is provided by the frictional force, which is जो frictional force के द्वारा provide किया गया. But if the frictional force is less than mv square upon r, then this frictional force is not responsible to make the car to turn along the curved road, and the car will move away from the road. So in this case, frictional force must be greater than mv square upon r. Now replacing it here, mv square upon r is less than equal to mu s. This is equation number 2. Mu s mg from equation second, and from equation second it will cancel out, and we can write it as v square upon r is less than mu s into z, and we can write it as v is less than equal to under root mu s gr. V is less than equal to mu s g upon r, means the velocity is equal to, while taking the circular turn, the velocity must be equal to under root mu s upon r, under root mu s gr, or less than under root mu s gr. But if the velocity is greater than under root mu s gr, then what will happen? Then the track, the frictional force between the track, railway, between the curved track and the tires is not sufficient to provide the centripetal force mv square upon r. Clear? So the velocity should be less than mu s gr to take the safe turn on the curved surface or the curved path. So we can write it as maximum Vmax velocity, to take the circular turn, it is less than or equal to mu s g. This is the maximum velocity for the safe turn of the car on the level road. This is the maximum velocity. Vmax is equal to, this is the maximum velocity. Below this velocity it is possible for the safe turn, but above this velocity it is not possible that car will take a safe turn on the curved path. So this is all about the circular motion of the car on the level road. Now we will discuss certain numericals based on this. Yes, dear students, look at the numerical in front of you and try to solve this numerical, which is based on the formula, but a little bit concept is here. Here the question says that the cyclist speeding at 18 km per hour. It is speeding at 18 km per hour on a level road, takes a sharp circular turn of radius 3 meter. There is a turn of radius 3 meter, and while driving 18 km per hour, the cyclist takes a sharp turn without reducing the speed. He is not reducing the speed, moving with this speed. The coefficient of static friction Mus is given. Mus is equal to 0.1. When the cyclist slip while taking the turn, it is asked that the cyclist will slip or not while taking the turn. So let us see that the cyclist will slip or not. It is given that velocity v is equal to 18 km per hour. It means to say that 18 into 1000 upon 3600. It will cancel out. 2 5s are 10. So it is equal to 5 meter per second. The velocity is 5 meter per second. Now mu s is given as 0.1. Mu s is, and r is given 3 meter. R is given as 3 meter. So we are knowing the condition. We are knowing the condition for velocity with which the cyclist will make a safe turn. Velocity with which the cyclist will make the safe turn on the circular track. The condition is that the frictional force is less than equal to mv square upon r. That is, the frictional mv square upon r. mv square upon r is less than or equal to f. mv square upon r is less than equal to f. This is the condition for safe turn on circular track. Safe turn for circular track. Now we will see here this condition is verified or not. This condition is verified. That is, mv square upon r is equal to less than, and we can write it as that mv square is less than equal to V square is less than equal to under root mu s rg. Clear? So this is the condition here. This is the condition. So we have calculated. So V square, and this V square can be given as 5 meter per second whole square, that is 25 meter square second square. And now mu s rg, we have to calculate the value of mu s rg. So it is equal to mu s 0.1 Clear, students? So look at here. We will check the condition. MV square with V square. So V square is equal to 5 meter per second whole square, and that is equal to 25 meter square per second square. And then under root mu s rg, that is equal to under root 0.1 into r 3 meter and g 10. It is equal to 10. V square is equal to mu s rg. Clear? So it is 3. So what you are observing that it is 3 meter square per second square. So what the value of mu s rg is less than V square. So condition not satisfied. Condition not satisfied. The condition of safe turn is not satisfied, and the cyclist will slip. The cyclist will slip while taking turn with 18 meter per second with the speed of 18 meter per second of a circular track of radius 3 meter and coefficient of static friction 0.3. If the cyclist is turning with the velocity of 18 km per hour, then obviously that cyclist will slip on the circular track. So that's all for today, students. And in the next topic, we will discuss about the cyclist moving on the banked road. Why banking is provided, what are the benefits of providing banking on the track. So that's all, students. Thank you. Have a nice day. Take care.